Okay, so last time we were talking about Avogadro, his number, scaling everything from the atomic level up to this mystical, magical mole, and how those moles were able to make it so that we could quantify and physically measure things. When you do this sort of scaling up, an interesting phenomenon occurs. So we had, let's see, I'm going to start this. So we had Avogadro. He takes atomic level and scales the physical level. Why did that thing just pop up? That's weird. So from what we can think of on the atomic level, you get a bunch of them. Now you can physically measure it. So this is your microscopic, and this is your macroscopic. Now in this scaling up, as I mentioned last week, we had something that looked like two H2s plus an O2 going to make two H2Os. And we used to think of this on the atomic level. We used to think of this on the atomic level. Meaning, we used to say two molecules of H2 plus one molecule O2 makes two molecules of H2O. So in the back of our heads, when we started doing and balancing all these equations, we were probably almost to the person thinking of this on the atomic level. Just a couple of molecules, we had another molecule, make a couple more. Now, all we're going to do is scale this up. Everyone is going to get multiplied by Avogadro's number. So instead of thinking about in terms of molecules, now we're going to think about it in terms of moles. Now we think in terms of moles, meaning 2 moles H2 plus 1 mole O2 makes 2 moles H2O. So now these coefficients out in front aren't just the number of molecules, but now they're the number of moles. So coefficients tell us how many moles of each compound we have. Now, I alluded to that last week. I just wanted to reformalize it here again, because we're going to start exploiting this whole balanced equation, input equals output, conservation of mass, and the fact that things can come together in small whole numbered ratios, and that one thing may combine with another to make compounds. We have now, well, actually, we already have, but we're continuing the journey of taking all these little pieces that we've been building on for 4 weeks and putting them together to make one large piece puzzle. Now, at the beginning of this class, I said that one of the things that we are going to do is to learn how to qualitatively explain what's going on. Day one, I said, we all know that if you heat up a gas or a balloon, it will get bigger. We know that as the temperature goes up, the volume will go up. We just know that intuitively or instinctively, but now we're going to actually start to get to the quantitative, and that is actually how much, how big will it get? Right now, we've just done the qualitative by saying we have, two hydrogens plus an oxygen making two waters, okay? That's the qualitative. We understand that part. Now what we're gonna do is move into the realm of how many hydrogens and how many oxygens will make how much water. First, we're gonna do it on a molar basis, and then we're gonna do the physical going in, weighing it out, and predicting just how much stuff we should get if we were to have done this reaction. So I'm going to rewrite this equation so we can have it on hand. So I'm going to scroll down and rewrite it, because what I want to point out is something that's probably already clicking in your brain, even though we haven't talked about it, and that is the ratio between each of these products and reactants. So let me rewrite it so we can have it on hand. So I had two hydrogens plus an oxygen goes to make two waters. Now the coefficients are the number of moles. The coefficients are the number of moles. So if we look at this equation right here, two hydrogens plus an oxygen make two waters. That means for every 2 moles of hydrogen, we need 1 mole of oxygen, and we'll make 2 moles of water. This allows us now to actually set up ratios of each of these in relation to another. So we're going to go back to our math terms, and we're going to set up 6 ratios, because there are 6 of them here. And so listen to the words as I write them. You have 2 moles of hydrogen per every, or for every, 1 mole of oxygen. So what does per or for every mean in math? You might recall
Divide.
that per, yeah, it means divide. So per, for every, for each, all of these terms mean to divide. So there are 2 moles of hydrogen per every 1 mole of oxygen. Well, you could take that same ratio and flip it around on itself, right? You could instead relate the oxygen to the hydrogen and say that there's 1 mole of oxygen per every 2 moles of hydrogen. Looking at that equation, again, we can look at it in terms of hydrogen to waters, and you would see that you have 2 moles of hydrogen per every 2 moles of water, or vice versa. 2 moles of water for every 2 moles of hydrogen. Now we've related hydrogen to oxygen and hydrogen to water, but there's still one more relationship that we can have up there. We can actually relate oxygen to the water. So let's go ahead and do that. If we look up there, there's 1 mole of oxygen for every 2 moles of water. Or you could look at it the other way. For every 2 moles of water, you would need 1 mole of oxygen. Now, each of these, what we call molar ratios, are nothing more than a conversion factor. We're going all the way back to the first exam where we did conversions. It's just a different kind of conversion. Instead of feet and inches and meters, it's just from one species to another. You'll see very quickly the reason why when we were doing our stuff last week, and I asked us to do these conversions here with the moles, and I said, hey, how do we do this? And I said, where are we going? And you say to moles. And I would always say to moles of what? Because now what we're going to start doing is not just figuring out the moles or the grams of one thing, but the moles and the grams of many things within one equation. So I'm going to ask an easy question before I show you the mathematics. If I have 2 moles of hydrogen, how many moles of water can I make?
On the team
2.
for the success.
2. If I have 4 moles of hydrogen, how many moles of water can I make?
2.
If I have 4.
4.
Together.
Oh.
Then
4,
2.
right? These guys are on essentially a 1-to-1 or a 2-to-2 basis here. So hopefully many of you who are sitting there going like, okay, wait, it can't be that easy. Yes, yes, it is. Until you actually use real numbers, right? So hopefully you can see that if I have 2 moles of hydrogen, I will need 1 mole of oxygen. I will make 2 moles of water. If I had 4 moles of hydrogen, I would need, let me use my cursor. If I had 4 moles of hydrogen, I would need 2 moles of oxygen to make 4 moles of water. I would just double everything. Now, if we use simple and easy and small numbers, that's not a problem. But let's go ahead and use real numbers and now rely on our conversion factors here, our molar ratios, to answer these questions for us. And again, I'm going to go ahead and start with what should be an easy one. Hopefully it is. And then we'll move to a more complicated one, and then we'll get to the cool conversion. All right, I'm going to have to unfortunately scroll up past this, guys. So hopefully you have your notes nearby, so you have that equation. But I'm going to ask the question: if 7 moles of hydrogen reacts with oxygen, how many moles of oxygen are needed how many moles H2O are made? Now, I've still chosen values that should be intuitive. You guys can do the math in your head. But let's see how it looks mathematically before we take a leap into some bigger numbers. Okay. The first question is, how many moles of oxygen are needed? So just like in any other conversion, we're going to come over here and write moles of oxygen. And then I'm going to ask, is there anything up there that looks like moles? That's right, 7 moles of hydrogen. Now I'm going to do one of 2 things. I'm either going to look at all these ratios here, or I'm going to look at my equation up here to look for how many of each of these quantities I have. So in the case of this conversion, we have to remind ourselves, just like any other conversion, what units go where. So since we have moles of hydrogen on the top, we'll put moles of hydrogen on the bottom and go to moles of oxygen on the top. So that way our units cancel top to bottom, leaving us with the units we want. So we go up here and we either find the ratio that has hydrogen on the bottom and oxygen on the top, or we go all the way up to the equation, which is what we'll end up doing, and see that I see 2 hydrogens here in the equation and 1 oxygen in the equation. Your molar ratios always come from the chemical equation, the balanced chemical equation. So with that in mind, there are 2 hydrogens to 1 oxygen, and you should see that that gives you 3.5 moles of oxygen. Our second part said we want to get to water. So we'll do the same thing. We'll put moles of H2O on the left. We'll put 7 moles of H2 on the right. Put our units of how we want them to cancel. Moles of hydrogen on the bottom, moles of water on top. Obvious answer is obvious, but let's go ahead and look at it. We have a ratio up here with 2 moles of hydrogen on the bottom and 2 moles of water on top, or we can look up at the equation and say 2 moles of hydrogen on the left and 2 moles of water on the right. So let's put in the 2 and 2. And we'll get 7 moles of hydrogen, or 7 moles of water. Gives you the amount of one thing in a balanced chemical equation, the amount. So the number of atoms slash the number of moles. You know the amounts of everything in that equation. If you know one thing, you know them all. All right. You guys seem like you're getting this pretty quickly. Let's step it up a notch. What if I have 3 hydrogens plus a nitrogen goes to make 2 ammonias? I'm going to pick a random number, so I'm going to have to do some calculations on the side. So slow us down. That's fine. We need to get slowed down here. I'm going to say if 17.39 moles of hydrogen reacts, how many moles of nitrogen are needed? How many moles NH3 are made? Now here it won't be as intuitive as it was with the water. Our ratios are a little off here, and our numbers are finally numbers that aren't easily multiplied and divided across. That's okay, we can still do this problem. We just have to set it up, knock it down. First question asks us for moles of nitrogen, so I'm going to put moles of nitrogen on the left. And we'll put our 17.39 moles of hydrogen on the right. Once again, we'll take care of our units first. Moles of hydrogen go on the bottom. Moles of nitrogen on top. And we'll go back up here to the top to see what our molar ratio is. So if we go up there, we see that we have 3 hydrogens and we have 1 nitrogen. So at the end of the day, you should end up with 5.80 moles of nitrogen. We can do the same now with the ammonia. So we're going to say moles of NH3 on the right. And we know that moles can look like moles. Just go to that equation, use the conversion, look at the ratio. 17.39 moles of hydrogen. Moles of hydrogen are still going to go on the bottom. We're trying to get rid of those. This time now we're going to go to moles of NH3. So we look back at that equation. Oops. No wonder your stylus might be broken. You keep dropping it. we see that we have 3 moles of hydrogen and now 2 moles of the NH3, and this should give you 10.6 moles on the other end. If you know the amount of one thing, you know the amount of all things. So far, so good?
I got 11.6 for the ball.
Sorry, 11.6.
Yeah.
I can't multiply correctly. I actually did that one in my head, so I just forgot to carry a 1 over. Sorry about that. But hopefully you guys are looking at this and going, this isn't so bad. And I hope so, because now it's going to get real. Because it's all fine and well to talk about things on the atomic level and think about them in terms of just little molecules reacting. It's a little weird to start talking about this mole, the 6.022 times 10 to the 23rd stuffs, because it gets to be stuff you can't really fathom. And it's even more of a thing to just go through and make molar ratios and be like, oh, okay, what does it all mean? And the reason why I say that is because I would say in a normal semester, you've never gone to the balance and weighed out a certain number of moles of things. Of course, you didn't actually do that this semester, but you get the idea. When you go to that balance, what do you measure out? You don't measure moles.
Usually pounds or grams.
Grams. And so what we really want this to lead to is something we can physically do, weigh something, do the reaction, and weigh it again and see, like, did we get what we should have gotten? And so that leads us to the coolest calculation we do in this class. And that is the so-called, or as I like to call it, mass to mole to mass. Now your book will probably just call this a mass conversion. If you look online, they'll just call it mass. I actually don't like doing that. I don't like doing that because I find it misleading or disingenuous. You can't just go from one mass to another. In order to go from one thing to another, you have to look at their molar ratios. We spent a week balancing equations. We just spent the last 30 minutes noting that there is a relationship between the number of moles, the amount of one species to another, whether it's reactants to products or reactants to other reactants. And this is the reason why. Because it's through this correlation right here of a balanced chemical equation that we can take a mass of one substance and predict the mass of another. So this is where we get to that quantitative, where we now go and say, if I'm going to use this amount of material, how much should I make on the other side? Here's how it works. What you do is you start with the mass of your given substance. So your initial weighing of something. Or I may say, you have this many grams of a reactant, how much product will I make? So you start with the mass that you're given. Then you need to convert that to the moles of the thing you're given. So how do we go from mass to mole? Simple, the periodic table. At the end of last week, we went over there and we said, hey, if we go to the periodic table, let me just move that here real quick so I don't keep going to the wrong spot. If we go to the periodic table, we can determine the molar mass of any substance and we can go from the grams to the moles. So what we're going to do is that very same thing. So we're going to go from the mass of what we are given to the moles. of that thing that we were given. And this is going to go from the periodic table. Next, I want to go from the moles of the thing that we were given to the moles of the thing we want. Notice that I'm putting those units in such a way that they will end up canceling. Masses of the given canceling top to bottom right now. Moles of what we were given now canceling top to bottom. Now we're starting to get to the moles of the thing we want. Now, to go from one species to another, to go from hydrogen to ammonia, to go from hydrogen to nitrogen, all we do is we go back up to whatever the balanced equation is, and we can see this molar ratio. So this is from the chemical equation. All we have to do now is get back out to the mass that we want. So we'll go from the moles of what we want to the mass. And again, to do this, we will go back to the periodic table. And at the end, we have the mass that we wanted in the first place. If you look at the top row, you'll see the words mass, moles, moles, mass. That's the reason why I call this the mass to mole to moles to mass calculation. And what this allows us to do is to go from any one thing that we've weighed out and now predict how much of the other reactant do we need? How much of the product will we make? We can do this before we even touch a chemical bench, before we even touch a piece of equipment. We should know what we're supposed to make, what we're supposed to use, and how much. This is probably the most powerful calculation we do in this class. I think this one is best done by example. First, we're going to have something ugly reacting with aluminum. That's my last time I get to make my Feo joke. Thank you for laughing, Frank. If you do this, this looks an awful lot like a single replacement. And I'll skip to the end on it for you and just tell you that the coefficients are 3, 2, 3, and 1. This is actually a way that you can take a rusted-like material, whether it's iron 2 or iron 3. If you stick some aluminum there, because of your activity series, if you stick them next to each other, you give them enough heat, you give them a way to do a little exchange, they'll do it. The aluminum will oxidize and it'll give you back your iron. Kind of cool. Okay. So here's my question on this problem. 14.4 grams of FeO needs how much aluminum, makes how much iron, makes how much Al2O3. Now, as we start to get into this problem, I want to point out some of the wording and how you can understand what you're being asked to do. Although with multiple choice exams, it'll be a little more painfully obvious because The units will probably be there for you. But let's go to the real life situation. I gave you 14.4 grams of FeO. When I ask you how much on this question, what I'm really asking for are the grams. If I give you a mass, I'll want a mass. Mass to mole to mole to mass. So that how much is the grams? I don't think I've ever asked a question, I may have once or twice, of how many moles. Usually that's just a way to get you guys, your feet wet as far as like looking at that molar ratio. Almost uniformly, if I give you a mass, I'm wanting a mass. And so, let's start this problem. Just like any other time, I'm going to write where I'm going. Grams of aluminum. And then I would ask you, is there anything up there that looks like grams?
Grams
And what is it, Frank?
of FeO. Of iron oxide.
14.4 grams of iron trioxide, the FeO. We can make a mass look like a mass. They're the same units. We just have to make it look like it. Now, there's a nice little mantra that can go with this problem and actually almost all the problems from here to the end of the class. This problem is a mass to mole to mole to mass. If I give you a mass, I'll want a mass. Mass to mole to mole to mass. So I actually, immediately when I see this, I say the words mass to mole to mole to mass. Every word I say, I draw a line. 3 boxes matches the 3 boxes I had up there. Coincidence? I think not. So now that we have our boxes, we know the steps we're going to take. We just have to do it. So I need to go from grams of FeO to moles of FeO. I'll notice if I have grams of FeO on top, that means the grams of FeO will have to go on the bottom. I wanted to go to moles of FeO. I don't want FeO, I want aluminum. So I'm going to put these moles of FeO on the bottom, and I will convert them to moles of aluminum on top. But I didn't want moles, I wanted mass. So again, playing with the units. Moles of aluminum on the bottom will go to grams of aluminum on top. Now, if you go to the periodic table, you'll be able to calculate the grams of FeO, and it will be 71.85 grams. How many moles is that if we went to the periodic table?
1.
1. There's always 1 mole on the periodic table. All right, so we've gone to the periodic table. Next, we go to the equation. So how many FeOs do you see in the chemical equation up there?
3.
3. How many aluminums do you see?
2.
2.
2. Okay, we're back to the periodic table to get ourselves out of this. So how many moles of aluminum are on the periodic table?
1 mole.
Always 1 mole on the periodic table, and aluminum weighs 26.98 grams. At the end, that should give you 3.60 grams of aluminum. I'll pause a moment in case some people are pounding their calculators to make sure they know how they the calculation is done, make sure they get the correct answer. All right, did anybody not get that number? Okay, I assume then that we all have that. So let's do the next one. The next one was how much iron, so how many grams of iron. So once again, we're gonna put where we're going on the one side, and we're gonna start, we might as well start in the same place we were. Gonna ask ourselves, is there anything that looks up there as grams of iron? Well, grams of FeO can look like grams of iron. So I give you a mass, I want a mass, 2 mole, 2 mole, 2 mass. Once again, just playing with the units. I don't want grams of FeO, so I'm gonna go ahead and put those on the bottom. I'm gonna go from grams to moles of FeO. I don't want those moles, so I'm gonna go ahead and put those on the bottom and transform them into moles of iron. And finally, I don't want those moles of iron, so I'm going to put those on the bottom and transform them into the grams of iron. I'll go to the periodic table. The mass of FeO is 71.85. And since it's the periodic table, there's 1 mole there. Let's look at the ratio. How many FeOs do you see up there? Three. And irons? 3. We'll go back to the periodic table. So 1 mole is 55.85 grams. At the end of the day, that should give you 11.2 grams of iron. Let's do the last one. Alan, your mic popped up. Are you about to say something, or was it an accident?
It was an accident. Sorry.
No one apologizes in this class. No one apologizes. It's all good. All right. So now we're going to go this time to aluminum oxide. And we're going to start in the same place, 14.4 grams of FeO. And this is a mass, 2 mole, 2 mole, 2 mass calculation. Once again, looking at the units, grams of FeO on top, better cancel grams of FeO on the bottom and convert that to moles of FeO. Cancel out the moles of FeO, put them on the bottom. Let's go to moles of Al2O3. And once again, cancel out moles of Al2O3 on the bottom and turn that into grams of Al2O3. Okay. I wonder what our first step is going to be. Pro tip is the same. If we're starting in the same place, our first steps are going to be the same. Just like if this were a normal semester and you guys were coming to school, your first steps to get here would all be the same. Your first steps to get anywhere would all be the same. First, you open your door, then you walk out to your car and you get in your car. You start driving, and that's all of this right here. You start driving, and the question is, where are you going? And that's this middle part. That's where you're going to make your decision about which direction you're going to go. Are you going to the supermarket? Are you going to school? Are you going to your friend's house? That will tell you where you're going. From there, it's child's play to get out. So, it should be no surprise then that there's 1 mole of FeO and it is 71.85 grams. And it should also be a no-brainer that it's 3 for the FeO. All of that is exactly the same because we started in the same spot. None of that should change. Now we just have to look up at the ratio. We have 3 FeOs and only 1 aluminum oxide. And the 1 aluminum oxide will weigh 101.96 grams. Give you something like 6.81. Again, I'm going to pause to let those who want to double check the calculator work to do so. Make sure we know we can do this calculation because we're going to do a lot of these. And we better be good at them and quick at them. So we want to make sure we're not all thumbs on our calculators. Did anybody not get those numbers? All right, one thing to note about this is that I actually didn't do the calculation on the last number. I never do. But I know that's the right number within experimental error or sig figs even. And how did I know the 6.81 was going to be the number?
You used one of the ratios that you already know.
Oh, there we go. What goes in must come out. You're right. I could have done that if I noticed that one was a multiple of another. In fact, that's exactly what I did right here. I noticed that I'd make twice as many ammonias as I would nitrogen. So I looked at this 5.8, did the mental math incorrectly, apparently. And I had 10.6 when it's 11.6. I just doubled it. So if you're clever enough and you can see one of these ratios that actually will allow you to do that, go with your bad self, or you can remember good old conservation of mass, right? If I had 14.4 grams of FeO and 3.60 grams of aluminum, that's what, 17, that's 18 grams on the left, which means I better have 18 grams on the right, conservation of mass. So once you told me that iron was 11.2, it fell out that aluminum oxide had to be 6.8 or by the number 6.81. It's okay. I just remembered my conservation of mass. Today, it should all fall out. If you know the amount of one thing, you know the amount of all things. It's really, really powerful. Okay, before I make this more difficult, anybody got some questions? All right, then let's take it one step further. Let's do a limiting reactant. As the name sort of implies, when you run out of an ingredient, read reactant. calculations we just did, whether by the Muller ratio ones or the FEO, assumes that I had the exact amounts of everything that I needed. That's like never the case. Oftentimes in chemical reactions, people will flood the reaction with a really cheap ingredient to make sure the really expedient is all used up so they don't waste material. Now, limiting reactant problems are exactly like what we just did, and it's something that we do every day. Now, imagine this. We're all in a classroom, and I'm asking you this question. You have 2 slices of bread, an entire jar of peanut butter, and an entire jar of jelly. How many peanut butter and jelly sandwiches can you make?
Just one.
Just one. You have an entire loaf of bread, the end scrapings of a container of peanut butter, and a full jar of jelly. How many peanut butter and jelly sandwiches can you make?
Barely one.
One. You have an entire loaf of bread, an entire jar of peanut butter, and the bottom scrapings of... How many peanut butter and jellies can you make?
Barely one.
Frank?
Barely
Just one. Why?
Limiting reactants.
Because in every one of these scenarios, what happened? You ran out of something. Now, what we just did there mentally in each one of those scenarios is we took all the ingredients and we very quickly calculated, okay, yeah, I guess with only 2 slices of bread, even though I have all the peanut butter and jelly in the world, I'm still making 1 sandwich. The second scenario, I have clearly enough bread to make like 12 sandwiches and enough jelly to choke a camel, but I've only got enough peanut butter for 1 sandwich. So in each one of these scenarios, you took each one of the ingredients and did the calculation to see just how many you could make. And at the end of the day, the one that gave you the least was the limiting factor, and that's how much you could make. Limiting reactant problems are no different than what we just did up here, except what it's going to involve is that you are given the amounts of 2 or more of the ingredients and asked to say, how much product will you make on the back end? And so just like with our little mental exercise of peanut butter and jellies, we're going to do this now mathematically. You're going to take each one of your ingredients on its own and calculate how much product you think you're going to make. At the end of the day, you're going to compare them. And the one that gives you the least amount is what you will make, and that's the ingredient that limits you. So, here we go. We have 3 hydrogens plus a nitrogen. One of my workhorse equations here. I like it because the ratios are not equal. What I'm going to do is I'm going to take 15.7 grams of nitrogen, 15.7 grams of nitrogen reacts with 7.81 grams of hydrogen. How much ammonia is made? You will recognize a limiting reactant problem because you'll be given multiple ingredients. In the one above, in the FEO, we were not given multiple ingredients. We were given 1 ingredient and asked to calculate just how much aluminum would I have to add, and then how much of each do I expect to find on the back end. Just to remind ourselves, when I ask you the how much, this means I'm looking for grams. So let's do this problem. in each of these for the grams of NH3. So I'm just going to go ahead and put it down twice because I'm going to do this calculation twice, one for each of the ingredients. So on the first one, I will start with my 15.7 grams of nitrogen. In the second one, it'll be my 7.81 grams of hydrogen. Now, as we do this, we see that we have a mass to a mass. So this is a mass to mole to mole to mass calculation. And the same on the bottom, mass to mole to mole to mass. We have our boxes. Let's fill them in. In the first box, on the first calculation, grams of nitrogen are on top, therefore I have to put them on the bottom. And I'm going to convert those to the moles of nitrogen. And we're going from the periodic tables, the equations, back to the periodic table. Moles of nitrogen is not what we want. We'll put that on the bottom, and we're going to convert that to the moles of NH3 that we want. But we don't want moles, we want mass. So moles of NH3 will convert to grams of NH3. So even before this, we know we've done this right because it's grams, moles, moles, leaving us at the grams that we want. All right, to the periodic table, Bella will tell me that there is only 1 mole of nitrogen. How much does that weigh?
28 grams.
How did you get 28?
14 plus 14.
Yeah, there's 2 nitrogens here, that N2. Yeah, and 14 is the molar mass of nitrogen, so multiplies it by 2 to get 28.02. How many nitrogens do we see in the equation? 1. Ammonia's? 2. The last step, we're going back to the periodic table, so 1 mole will give you 17.04 grams of NH3. If you do that, you'll get 19.1 grams of NH3 if all the nitrogen were used up. Let's do the same thing down below. Grams of hydrogen are on top. Let's put those on the bottom to get rid of them. Let's turn them into moles of hydrogen. We don't want the moles of hydrogen on top. We'll put them on the bottom. Moles of hydrogen, and we'll convert them to moles of ammonia. And the last step should look exactly the same. We're ending at the same place. Okay. So, going to the periodic table, of course, is 1 mole. Not even going to worry about it on the back end there. Grams of hydrogen, there's 2 of them. Hydrogen weighs 101, so H2 weighs 202. There were 3 hydrogens to 2 ammonias, and our molar mass still stays the same as 17.04. If you do this, hydrogen would have given you 43.9 grams of ammonia. Now, at the end of the day, what does this mean? It means that even though you started out this reaction with what appears to be a whole lot more nitrogen than hydrogen, because of the molar masses, because of the molar ratios, it turns out that nitrogen will not give you the most bang for your buck. It's the one that's limiting you. So when you do this problem and you just check it with both of them, this is how much is made. And this guy limits. In limiting reactive problems, just do the problem twice, or do the problem with each reactant separately. The lesser amount is what you make.
So does that mean we would have just extra hydrogen after the reaction?
Yep.
Okay.
Yep. So, and if you stick around after, Miguel, I can actually show you the type of problem we would do in Chem 120, which is where we'll figure out just how much is left over. I won't expect you guys to do it here in this class, but it's only one more calculation, and it's kind of cool because this is what people do in real life. As I said before, you may flood the chamber with all the cheap stuff to make sure your expensive stuff is all used up, so you don't waste any of that. But you don't want to be completely wasteful. So what they do is they actually end up calculating how much is going to be wasted and try to get that number down by decreasing the excess of the cheap ingredient. You never go one-to-one. You never only use exactly what you want, because reactions have a nasty habit of not giving everything you want. It's called a percent yield. In fact, that's the last topic we'll talk about today is what does it mean when you don't make everything you thought you should have? Well, Mother Nature has lots of taxes along the way. And one of them is sometimes she doesn't give you everything you thought you would get. Maybe there's a side reaction, or maybe you just didn't harvest all of your product correctly. Maybe you lost some down the drain or something. So that's where percent yield comes in. And so our last little topic for the day, to give you guys a little more time to bone up for the exam here. So the percent yield. This is when you don't get everything you thought. When you do not get or make everything you thought. I think this is the last time we see percents, but they're all the same. It's the part over the whole, or what you actually got divided by what you theoretically should have gotten. So percent yield is equal to what you actually got. Of course, this is in grams, over your theoretical amount, also in grams, because percents are unitless. And of course, times your 100%. This calculation is easy enough to just say that if in the previous problem, you only made 18.73 grams of NH3, what is your percent yield? Now, in this case, it will have assumed that you've gone through and made some sort of calculation, whether it's a limiting reactant problem or whether it's just a straightforward, hey, I gave you an amount, how much did you make? At the end, someone will say, yeah, you didn't quite make everything you thought. So how much did you make? What's your percent yield? So your percent yield is equal to what you actually harvested, 18.73. Thank you, buddy. 18.73 divided by that 19.1 grams that you thought you were going to make, but you didn't quite, times your 100%, and this will end up with a 98.1% yield. So something somewhere went wrong, whether the reaction itself just didn't go to completion, whether you just didn't capture all the ammonia, whatever the reason, you didn't end up with what you thought, so you only had a 98% return. That's okay. In organic chemistry, it's usually because a reaction went sideways in a direction you didn't want to go. Friend in grad school whose percent yield of single digits was considered to be good for that reaction because of all the ways it could go south. Most of the time, reactions get into the 90s pretty regularly because we can control the conditions, especially for inorganic reactions. I would note that one of the labs that we're not doing, the baking soda lab, is a prime example of this. So, note, baking soda lab, which we are not doing. We're not doing it because no matter which way Dr. Hansen and I tried to make this lab anything more than staring at some white powder and looking at white powder and weighing white powder and giving you numbers about white powder, everything was lost. You either had to physically be there and see it to understand it, or there was no point in doing it. So we cut the lab, but which I would really encourage you guys to do. The baking soda lab is a prime example. It's a prime example of percent yield and these calculations, these mass to mole to mole to mass. I would recommend doing the pre-lab and the post-lab. And if you want, if you're one of those super go-getters, you can send me a little Zoom request and I can actually make some fake data for you to just try it out if you want. Baking soda lab, which we're not doing, is a prime example of percent yield and these mass to mole to mole to mouse calculations. I would recommend doing the pre and post lab. Practice. All right. So we've done a few things here this morning. Before I stop here, because I think that this is a good stopping point, are there any questions before I stop the recording?